These slides will describe how to quantify the pressure of a gas sample present in a column of gas. For example, imagine that you have the atmosphere column of pressure above the surface of the sea, and we ask the question, how does the pressure of the atmosphere vary as we travel from the surface of the ocean into the space? And so this is a good problem to work with to understand how the pressure changes with height in our day-to-day life. And so let's start with the issue that the atmospheric pressure depends on height. This is sort of our experience, and we ask the question: does it increase, or does it decrease, or how does it change as we travel from the surface to the sky and into the space? And so we can quantify this using simple expressions on the ideal gas law in the following manner. Let there be a gas column of certain height and has an area of cross section represented by A. This blue cylinder on your right gives you the column that we are assuming to be present, and we will assume that the bottom of the cylinder is at the surface of the ocean, sea level, and we have certain height z, and if you take a cross section at the height z from the ocean surface, we have, let's say, a pressure P, and now we consider a small increment in height from the height z to z plus dz, or a small element dz, the increase in the height. As the height increases, we ask the question, what happens to the pressure? In order to compute the pressure at the height, say z plus dz, we will see that we have certain mass dm between the height z and z plus dz. So we'll assume P is the pressure at height z, and then m is the mass of the gas column above the height z. Okay, m is the mass of the column above height z, and A is the air cross section, as I mentioned before. Let temperature of the gas be constant and independent of the height. And this is an important assumption. If we assume the temperature of the gas is changing, it gets more complicated and to calculate the effect of height on pressure. And let dP the change in the pressure with height dz. And so we will now start work things through and say, now if you travel from height z to z plus dz, where dz is a small infinitesimal change in height, the pressure will change from P to P plus dP, as shown in this picture. P plus dP at the pressure at the height z plus dz, shown on the right side here. And so the mass above the height also is changing. As we travel to higher and higher heights, the mass of the gas above that height of the atmospheric column is decreasing as we travel up, right? So the mass of the gas at height z is m. We defined that before. Now the mass of the gas above the height z plus dz will be less, because now we're traveling up, and therefore we are subtracting certain mass from m. So that will be m minus dm. Again, it is infinitesimal change in the mass. Okay, so we are saying that the pressure is P at height z, and is P plus dP at height z plus dz, and the mass of the gas above the height z is m, and mass of the gas above z plus dz is minus dm. Now one might ask the question, well, we are traveling up, therefore we have less and less mass of gas impinging its pressure on us, and so m minus dm is correct. And we are traveling up, therefore the height is increasing, so it's z plus dz is correct. Now what happens to the pressure? Now when we go up, we say that, well, the pressure actually decreases from our experience, but it's not necessarily established here. So we will simply put the pressure at height z plus dz equals to p plus dp, not p minus dp, because we have no idea what would happen if the pressure increases or decreases as we travel up. So it's safe to put a plus sign here explicitly, and if it so turns out to be a negative sign, so be it, and that will be the outcome of our mathematical calculation. So this is a very important point to recognize, and oftentimes the mistakes are made here. And so the pressure, we're not going to assume is going to drop, although that's our experience. We're going to consider that it will be p plus dp. Remember, the dp could be numerically equal to minus dp at the end after we have done our calculations. So you keep that in mind and move on. And so since pressure is force divided by area, we can easily calculate the pressure at different heights. So for example, pressure at height z is equal to the mass of the gas above that height, which we defined as equal to m, multiplied by the acceleration due to gravity, small g, divided by the area cross-section of the column A. So P equals to mg over A at height z. Now if we were to now travel from z to z plus dz, the pressure at the height z plus dz is then equal to P plus dP, and that's given by m minus dm times g. And so now we used m minus dm because we have traveled up through the column, and therefore we removed certain mass from m, and that mass is dm that we subtracted for the mass m. Therefore we have m minus dm multiplied by g, acceleration due to gravity, divided by a, as usual. In the next slide, we are now continuing to build our arguments, and so p minus p plus dp, now we're just subtracting the two terms from one from the other to get the value of minus dp. So p minus p plus dp in parenthesis equals to minus dp, and that's simply equal to mg over a, which is what we calculated for pressure at the height z to be, minus pressure at the height z plus dz, and that is m minus dm times g divided by a. So now we can cancel mg over a in the first term with mg over a in the second term, and therefore all that remains then is dm times g over a. So now we have managed to relate pressure, more precisely infinitesimal change in the pressure, with the infinitesimal change in mass multiplied by the acceleration due to gravity and divided by the area of cross-section. So now we have a function relates the pressure with mass. Now, however, we're looking for a relation that between pressure and height. So we need to find a way to connect the change in mass with height. Then we can relate all these together. And we can do so by simply understanding we have area in the bottom, and therefore area can be written in terms of volume times height dz. Therefore we can relate dm to the density, and then that can be related to the pressure in the following manner. And so the density is defined as dm over dv. Rho is the symbol for density. dm over dv is the rate of change of mass with respect to volume, right? So mass per unit volume. Or we can write dm as equal to rho times dv. So now dv is equal to now area cross-section multiplied by dz. So now we have related dm to dz. So small change in the mass is related to small change in the height. So now we can go back and substitute in the above expression for dm, and therefore then we can get minus dp, so change in the pressure as we see it, is equal to g over a, as we have seen previously, multiplied by dm, and now the dm is equal to rho times a times dz. Therefore, a and a can be cancelled out, and therefore we get minus dp as equivalent to g, the acceleration due to gravity, rho, the density of the gas, dz, the change in the height of the gas column. So now one could argue, well, why can't we just integrate on both sides and we get how an expression how pressure changes with height z? Well, a moment of thought realizes that the rho is the density of the gas may not be the same throughout the column from the bottom to the top. So integration of the equation requires that density be constant. If the density is not constant, then we need to express the density also as a function of height. And you can now remember that if I have a gas column, the pressure is changing. As the pressure changes, we know that the density of a gas changes. We have shown that in the previous slides. In fact, we're going to use that expression here to replace rho in terms of pressure shown in the next slide. And then we have the expression that we need to integrate and get the final answer we're looking for. So we have, just to summarize, we've shown that minus dp, the change in the pressure, is now equivalent to g times rho times dz. So the relationship with pressure, height, and density is where we left off on the last slide. Now we'll continue. Since the gas density changes as we travel from the bottom of the column to the top of the column, or anywhere in between, we will explicitly write density as a function of pressure, which we have done that before, as I mentioned before. Now just to recall, we wrote PV equals to RT. From that, we wrote P equals to W over M, that is N, the number of moles, 1 over VRT. And so now W over V is nothing but density, rho. Therefore, pressure equals to rho over M times RT, is what we worked out in the previous slides. And so now can write rho as equal to Pm over RT. So simply go to that expression on the right-hand side top corner. Minus dp then equal to g times pm over RT multiplied by dz. Now we're going to simply integrate this expression. Why? Because g is constant, m is constant, r is constant, t is constant. Therefore, we have dp on the left-hand side, p and dz on the right-hand side. So we will take the p from left-hand side to the right-hand side, from the right-hand side to the left-hand side. And then we have the expression 1 over p dp with the negative sign equals to gm over RT dz. Now we're going to integrate the two expressions with appropriate limits. Now we asked what would be our limits. Let's assume that P0 is the pressure of the gas at the bottom of the column. The bottom of the column, the height z equals to 0. So the lower limit on the left-hand side integral is P0, and the bottom limit on the right-hand side integral is then 0 because it's 0 height. Now P will be the final limit on the left-hand side because that's the integration we're doing, P0 to P, and therefore on the right-hand side the integration is going to be 0 to z. P is the pressure at the height z. Remember, that's how we have defined. So we have a negative sign on the left-hand side integral. We have a positive sign on the right-hand side integral. Now we can now easily integrate this because 1 over x dx is the integral which you have learned in your calculus, and therefore we can write that. On the right-hand side, it's a simple integral dx. Therefore, we write the integrals and with their limits, and we come back with this expression minus log p over p0, the integral on the left side, equals to g z m over RT. Now, if you have any difficulty in integrating the above expressions, please go back, look at the math details, look at your integral calculus, find out how to set limits, find out how to integrate simple functions such as 1 over pdp and dx in these cases. So we can now show that we have a logarithmic relationship between the pressure and the height. I will rewrite this a little bit, slightly different way, and absorb the negative sign onto the other side. So P over P0, right, will be equal to e to the power minus gzm over RT. So P over P0 I can write as equal to P is then equal to P0 e to the power minus parenthesis g, acceleration due to gravity, z, the height of the gas column, m, the molar mass of the gas, divided by RT. R is our gas constant, T the temperature. Now, what we have done, we've shown that the pressure of a gas in a gas column depends on height, and it is dependent on height exponentially, and it's dependent on height as decreasing exponentially, right? And so as we travel up, pressure drops. And this is the quantitative relationship, and this is referred to as the barometric law. Now let's analyze this equation in different ways and try to understand what it is telling us. On the next slide, I have written this: P equals to P0 e to the power minus gzm over RT. And we will look at it from different perspectives. For example, you plot pressure as a function of height. So what do we learn from that? The pressure should exponentially decrease with increase in height. Therefore, we write P on the y-axis, Z on the x-axis, and a smooth decrease, exponential drop in the pressure. Therefore, write that P equals to P0 e to the power minus mgz over RT. This is a very easy way to remember and familiarize your understanding of this equation. Just like a first order reaction, this expression is very, very similar to a first order kinetics reaction, if you remember that from previous classes and so on. C equals to C0 e to the power minus KT. Remember that. So lots of natural processes that we know of follow this kind of an exponential decay. And we also refer to this as the first order process. And we'll learn more about this and why these are really exponential intrinsically in later classes. Now we'll also worry how we're going to plot in a different way. Can we plot it in terms of a log scale? Yeah, so on the previous slide, we have a logarithmic relationship. So we can plot log P over P0. Okay, this is a natural log. P over P0 is a function of Z. Now we know from the previous slide expression we have written, it's going to be a linear expression. And so linear lines to be drawn. And we have, however, slope negative slope. So if you looked at the equation from the previous slide, you'll see the slope has to be negative. Now all that thing I have done is now to show the effects of temperature in here. So look at the top expression, and if the temperature is higher, then means that we have the negative exponent as a smaller value, right? Because temperature is in the denominator of the exponent. As the temperature increases, the value of the exponent becomes smaller and smaller. As the exponent becomes smaller, the function, the exponential function, is decaying slower and slower. Therefore, the slope, which is minus g z m over RT, is going to be small. So as t increases, the value of this fraction becomes smaller, therefore the slope becomes smaller. So that is high temperature, we have the red line. And in a converse manner, you can say at low temperature, you'll have the blue line. So in other words, depending on the temperature of the planet, the barometric law predicts how the pressure is changing. So if you apply this to planet Earth, you may get one slope. And now if you apply to the Venus, planet Venus, has a much higher temperature, room temperature. I mean, if you call that as room temperature, then it's the pressure is going to drop much more slowly with increase in height. So this is kind of a nice and neat example to show how the temperature has an effect on the change in the pressure as we travel upwards. In a very similar manner, the molar mass of the gas also affects. Now notice that the molar mass m is in the denominator of the exponent. So as we increase the mass m, the value of the exponent is increasing. As the value of the exponent increases, the function is going to decay much faster. Therefore, if I were to plot log p over p0 as a function of z in this third plot, we still get a linear function because you're plotting log versus z. However, the molecules that are heavier are going to have a larger slope, and so they decay much faster. The molecules that are lighter are going to decay much slower as a function of height. Therefore, you have a blue line that is above. And so this has important consequences. So if I have a mixture of gases that have, say, high molecular weight and low molecular weight, as we travel from the surface of the planet higher and higher, the composition of the atmosphere is going to change. As we go higher and higher, this plot predicts the heavier elements will settle down to the bottom and the lighter elements will be on the top. So this is a kind of nice thing to intuitively understand what's happening. So in our atmosphere, we have nitrogen and oxygen as the primary two components, and therefore the composition of nitrogen to oxygen, or the ratios, mole ratios, should change as you travel from the surface of the planet into higher heights. So think about this, how that might affect us when we make such travels. So pressure decreases more rapidly for heavier gases, that's illustrated by the last plot. Will there be less oxygen or more nitrogen as height increases? It's a kind of a reflective question to ask. So in summary, we show that the pressure decreases exponentially as we travel to higher heights from the surface of the planet. The pressure decrease in height depends on the molar mass. If the molar mass is higher for the gas, it decreases much more rapidly. And it also depends on the temperature. If the temperature of the gas is higher, it decreases much less rapidly than if the temperature were to be low. So these are the three important conclusions we can draw on how the pressure is related to the height. In real terms, if the change in height is very small, then the change in the pressure is not going to be substantial. So think about if you were to be working at the 100th floor of the Empire State Building, you take the elevator every day from the bottom to the top and from the top to the bottom of the building. How would you experience? What would you experience? Okay. And so assume the temperature atmosphere column is the constant in this particular case, but that's okay for now. So one other question I would like to ask is, why do athletes train in Denver, Colorado, the mile-high city? Think about it. You may have find the answers for this in many locations, but I would like you to interpret those answers in terms of the pictures above. So some examples and some problems, as usual. Give an example of daily life of the barometric law if you work at the Empire State Building on the 100th floor, for example. Work out 3 problems from the book which utilize the barometric law.